How's it going, all you YouTube synth heads? My name is Clint Hoagland, and this is Creating Electronic Music with ChucK. In our last video, we talked about how ChucK uses the extends keyword to create subclasses, and we saw how we could use that, for example, to make an oscillator that could use a note number instead of a frequency. In this tutorial, we're going to talk about Chubgraphs, which are a special class in ChucK that is designed to be overridden in that way. They're meant to act as a parent class so that you can extend them. I'm going to show a couple of simple examples that illustrate how Chubgraphs work, and then we're going to use a Chubgraph to make a flexible and reusable monosynthesizer modeled after the Moog Grandmother. So here's our standard super simple test setup. I've got an oscillator going into the DAC, turn it down a little, set the frequency, and let's hear it. Now let's stick a Chubgraph in between the sine osc and the DAC. If we play it back, we don't hear anything. That's because a Chubgraph has two very special members that let it do what it does, and those are called inlet and outlet. Let's make a subclass of a Chubgraph called a pass-through, and in our definition of that subclass, let's say that inlet connects directly to outlet. Let's replace our Chubgraph with that subclass and play it back. Now we can hear our oscillator again. If we try to imagine a Chubgraph as a physical device, that physical device would have an audio in, an audio out, and in between those things, you can wire up anything you want. I don't have any inside information on how they named these Chubgraphs, but I'm guessing it's something like this. In math, graph theory is the study of connections between objects. In the general case, the objects are referred to as nodes, and the lines connecting them are referred to as edges. Let's take a map of interstate highways in my home state of Michigan. In graph theory, the cities would be represented as nodes, and the highways would be represented as edges. Let's take a look at a guitarist's pedal board. The pedals can be represented as nodes, and the cables can be represented as edges. So this is starting to feel familiar, right? In ChucK, one way to think of UGen is as a node in a graph, and you use the ChucK operator to create an edge between two of those nodes. So if you picture all the UGens in a ChucK virtual machine as edges and nodes in a graph, then if you wanted to cut out a region of that graph, you might call that a subgraph, and if you wanted to make that a Chuckian pun, then you'd call that a Chubgraph. Like I said, I don't know for sure that that's why they call it that, but that's my educated guess. Let's switch our oscillator to a sawtooth so that we can hear this next part working a little better. So like we saw before, we have our saw oscillator, which is wired up to our pass-through, which is a subclass of a Chubgraph. Samples from the oscillator go in the inlet of the pass-through and then back out of the outlet. Let's stick a low-pass filter between the inlet and the outlet and set the frequency of that filter. If we play it back, we can hear that the filter is working. We can insert stuff into the overall Chubgraph by inserting them into the Chubgraph. Let's add a delay inside the Chubgraph after the filter. We'll set up the max, gain, and delay values, and then we'll chuck that delay back into itself. Then we also chuck the filter directly to the outlet so that we hear both the delayed signal and the signal without the delay. This thing should probably not be called a pass-through anymore, so let's rename it to a low-pass delay. So one thing that we notice here is that this delay is in mono. I am, as you know, a big fan of stereo delay. It turns out, based on a GitHub issue going back to 2016, that Chubgraphs are mono processors and that they do not support stereo on their own. This seems like quite a limitation until you think about how normal instruments usually start as mono and only become stereo after effects are added. The good news, though, is that, as we noted a couple of videos ago, all you have to do to support stereo operation is to create two of our low-pass delays in an array, and they automatically become a stereo pair. Let's change the delay time on one side of the array. Boom, stereo delay. So one thing I'll observe is that things like delays are kind of a pain to set up. There's a bunch of boilerplate that you have to type every time. If you have a favorite set of effects that you'd like to reuse, or even if you just want a stereo pair of two of the same thing, a Chubgraph is one way to only have to type all that once, and then you can reuse it forevermore. And if you use the score CK/initialize CK pattern that is suggested in the scores video, then you can add those Chubgraph subclasses to your ChucK VM during your initialize step, and then you never have to write that stuff again. So now let's turn our attention to the problem of creating a fully featured synthesizer voice. The idea here is that there's a typical arrangement of sound modules in a typical analog-style subtractive synthesizer. So we're going to arrange a set of UGens that mimics that arrangement so that we can have a reusable standard synth voice. We're going to model our synth after the Moog Grandmother synth, mainly because those do have a typical arrangement of modules and also because it's clearly labeled so it helps explain things. Note that ChucK does come with a Moog UGen as part of the C++ Synthesis Toolkit, or STK. I'll go over the SDK in more detail in another video. Suffice for now to say that you're welcome to use that one if you want, but I like the sound of the one we're going to build better. Let's turn the layout of modules on the front panel of a grandmother into a graph of edges and nodes. We're going to start simple and then add some richness as we go. The typical arrangement I was referring to before is this. Sound starts at an oscillator, passes through a filter, and then passes out through an adsr and then out of the audio output. Let's start a new subclass of the Chubgraph and call it a synth voice. Very first thing, let's give it a sawtooth oscillator and pass that into the outlet. Note that this synth doesn't make use of inlet, at least for now, and that's okay. In our ChucK script, we can now use the synth voice as a type. Let's wire it straight to the DAC and chuck some duration into now. Okay, now that we have that, let's put an adsr in there after the oscillator. In an analog synth, these are called voltage-controlled amplifiers, or VCAs for short, and they're usually the last thing before the audio out. Let's wire up some default values, and then we use the voice's inner adsr's key-on function to activate it. So it's kind of ugly to have to reach in too deep like that, so let's make a helper function inside synth voice that kicks the adsr's key-on function. It would be nice if this key-on function took a note number, so let's add that. In this way, we can send a MIDI note number to the synth voice's key-on function, and that will both change the pitch and start the adsr. Note that you can either pass the note number inside the parentheses, which feels like a typical C-based programming language, or you can use the ChucK operator instead. Okay, so now synth voice has an oscillator going into an adsr. Let's stick a low-pass filter in there next. In a real analog synth, the filter comes before the VCA, so let's stick an LPF between the saw osc and the adsr. Let's give that a default setting of, 500 Hertz. If we play it back, we can hear it working. Now, it's typical for analog subtractive synths to have a filter envelope in addition to the envelope on the VCA. Depending on the synth, that might be an independent envelope, or it might be the same envelope. On a Moog Grandmother, you can select an envelope amount, and that governs how much the VCA envelope affects the filter cutoff. Let's steal that design for ourselves. Let's say that for now, by default, our filter envelope amount is 500. So how do we wire the filter cutoff up to the adsr? One thing that jumps out at me as we're thinking about this is that the adsr has got to affect the VCA amplitude and the filter cutoff simultaneously. When you want simultaneous things to happen in ChucK, that suggests that you might want a second shred. Let's spork a function and call it filter envelope. Inside this function, the first thing we want to do is store off the frequency that we had when the envelope starts. I'll call that start freq. Then we need to somehow track the position of the adsr until it finishes. Luckily for us, the adsr UGen has a .state property that you can query. It has 5 states, 0 for the attack stage, 1 for the decay stage, 2 for the sustain stage, 3 for the release stage, and 4 once the entire envelope is completed after the release stage. So since that's the case, we can start a loop here that says while adsr.state is not equal to 4, we want the filter to track what the adsr is doing. Now, how do we do that? We want to multiply our filter envelope amount by adsr.value. It's tempting to try to use the adsr's .last property, but that's not actually what we want, and I'll show you why in a minute. For now, let's just add that multiplied value to the start frequency and chuck that to the low-pass frequency. Then let's chuck a little time into now for each loop iteration. Let's crank the attack a little bit so that we can hear it working. Okay, so why did we use .value instead of .last? Let's throw in some logging statements to see what's happening. I'll add a statement for state, last, and value. So if we look at the state and the value, as it reaches the end of the attack stage, value rises to 1. Last does something else. If we continue to scroll down, .value is descending in an orderly fashion while .last is kind of jumping around, including to negative values. This is because .last is the value of the last audio sample that came through the adsr and not the adsr's position. The adsr's position, as we can see, is held in the .value property. You might be asking yourself, how in the world did I figure this out? The answer is that it's in the UGen reference online. This is the URL for that, or if you Google ChucK UGen reference, it comes right up. Then you can just scroll to each UGen to find out what its properties are. One thing to note is that, hey, .value isn't listed under adsr. That's because adsr extends a parent class called envelope. Recall from our previous video that subclasses have all the capabilities of their parent classes. adsr gets a .value property because it extends envelope. Now, if you were paying attention 2 minutes ago when we said that there were 5 states starting at 0 and ending at 4, you might have noticed that my state never got past 2. This is because of the way we are calling new notes. We are calling key on, but we never follow it with a corresponding call to key off. This is the equivalent of pressing down on a key on a piano or organ and then never lifting your finger back up. Ordinarily, that's not a problem. You're dealing with a single adsr generator and you're just resetting its stage back to 0 over and over, no harm, no foul. However, in our case, we just did something really bad. We sporked a new shred, and in that shred, we said continue on in an infinite loop until the adsr reaches a state of 4, which it never does. And that means that every time we play a note on our synth voice, we create a new shred that never exits. I'm trying to make a video here, so I'm not going to even try to find out what happens when you make an infinite number of shreds. One plausible outcome is that ChucK is smart and limits the number of shreds in a VM. Another plausible outcome is that the number of shreds grows until your machine runs out of some resource and your computer reboots. So you're welcome to try that on your own, but I'm going to try something safer. I could just rely on the user always taking their metaphorical finger off the key and assuming that every key on will be followed by a key off. But that's not very user-friendly, so let's make it harder to screw up. I'll change my if check so that it exits if there's ever a moment that the state is not 0, but the value is 0. Put another way, if the value is ever 0 after the attack phase finishes, we'll assume the shred should end. We test that out with our logging statements, and we can see that the shred ends after the decay stage. Much safer, and it still gives us the flexibility of using the sustain and release stages if those keep the value above 0. Let's test that by making the sustain 0.5. We can see very clearly that our adsr got to stage 2 and then held the value at 0.5. Okay, before we add any more features, let's make this a little easier to use. We're going to add 3 functions, and they all work basically the same with minor differences. I had to test some stuff out, so you won't see me type these. The first is called cutoff. It takes an amount. We'll write 2 if checks, one to make sure that you don't send an amount more than 100, and another to prevent an amount less than 0. Then we multiply that value divided by 100 times 5,000. We chuck that into a thing called filter cutoff. Now, I added filter cutoff because there's a lot of problems with using the filter's freak value for things in real time. I'll show you that in a second. At the bottom of this function, let's chuck 10 milliseconds into now. I'll show you why in a bit. Now let's jump up to where I added filter cutoff. You can see that it's just a float, and I chuck it right into lpf.freak. In our filter envelope, I change it so that filter cutoff gets chucked into start freak, and I chuck 10 milliseconds into now immediately afterwards. The reason I had to add those is that there's something I don't quite understand about ChucK concurrency that's related to my use of a spork for a filter envelope. If I take those two 10 millisecond waits out, something bad happens. It seems to start bouncing back and forth between its initial value and the value it's supposed to be. So for now, I'm leaving them in. So here I changed my script to bounce around a major chord with some major 7ths and 9ths going on. Here's what it sounds like if I randomize the cutoff. I copied my cutoff function and made a res function. It's just the same, except it multiplies 20 times the amount and then adds 0.3 to the result. It chucks that into the lpf.q property. Now let's randomize that. Lastly, we make a third function that is just the same as the other two, but we'll call that env, and that just changes the filter envelope amount up to a total max of 5,000. Let's comment out the random cutoff and instead use a random envelope amount. Let's change our initial cutoff so we can hear it better. Okay, for the next feature, I decided to take on what's happening on this blue panel. You can do a few things here, but I'm particularly interested in the fact that there are two oscillators. You can choose their frequency relationship, and you can also choose the waveform for each one. I did a lot of typing to make this work, but it ended up pretty cool. I started by renaming my osc to saw1, then I added a second saw1 and chucked that into the same filter. Then I declared two triangle oscillators and two square oscillators. I set an initial gain for all of these. I added in a new float called detune and an int called oscOffset. I added a function called setOsc1 frequency and another called setOsc2 frequency. As you can see, these just set the corresponding oscillators to that frequency. Then in my keyOn function, I now call those instead of setting the frequency directly. Note that for oscillator 2, I also add in the oscillator offset and the detune value. Then I have these two very big but very simple functions called chooseOsc1 and chooseOsc2. As you can see, these take a value between 0 and 3. 0 unchucks everything from that oscillator, 1 hooks up the triangle oscillator, 2 hooks up the saw, and 3 hooks up the square. Finally, I added another helper function to make it so that the detune goes from 0 to 100. So here's how this thing's sounding now. I changed my notes array so that it's just an octave and a seventh. I set my cutoff to be 10 here. I chose saws for both my 1 and 2 oscillator. They're detuned by 10 out of 100. Their offset is 0. And then let's hear how it sounds just like that. I've got a random amount of envelope happening here, and we're playing some 16th notes. That sounds pretty nice. Let's add some random resonance. Not bad. All right, let's choose a random oscillator from a triangle or the square or the saw for every note. Let's go back to just being the saw, and let's turn down the speed a little bit, and let's add an attack time in, and let's change the voice offset to 7. See how that sounds. Actually, that kind of sounds better if the resonance is always low. Let's see how that sounds. Or we could make this like a longer thing and make this like 2 seconds in and out. And let's try the random oscillator thing with that. Let's actually make the decay time happen too. So I can imagine throwing that into some delays and reverbs and stuff might sound kind of cool. Okay, there are 5 things left in the Moog Grandmother that our Chubgraph synth voice does not yet do. It has an arpeggiator, it has an LFO, it has a noise source, it has a high-pass filter, and it has a spring reverb. Of those, we're not going to do the arpeggiator/sequencer because that doesn't really make sense to do in ChucK. Making an arpeggio or sequence in ChucK is simpler than just playing a melody. So let's do an LFO. Once again, this involved a bit of messing around and a lot of typing, so I'll just go over the changes. Okay, to start, we now have a sine osc called sine LFO, a saw osc called saw LFO, a square osc called square LFO, and by default, the sine LFO goes into a gain called pitch LFO, and also into a gain called filter LFO, and those both go into a black hole. The reason why I made these two things, these two gains, is so that you can change on the fly the amount of LFO you want to apply to your pitch or to your filter. And then I made a function called set LFO frequency, and that makes it so that you can all at once set the frequency of all those different oscillators. And by default, I'm setting that to 6. And I'm setting the gain for the filter LFO to 0 and the pitch LFO to 0 as well. Now I send a 2 into all of our oscillators that were part of our signal chain up here. And that is to accomplish them, the LFO will then be doing frequency modulation, as we saw in our oscillator sync tutorial. And then I'm chucking the pitch LFO into all of those oscillators so that they are all experiencing frequency sync coming from this gain, so the LFO goes into this gain and then out into these. So they're set up to pitch a frequency track that gain thing. All right. Next, these are things that were here before. Next thing here is that I made a function called process LFO. And while this is true, our filter cutoff, which is governing the filter cutoff that we had in our filter envelope, is that's being multiplied times the filter LFO dot last, which, remember, filter LFO is actually the gain module, so that will be getting the adjusted amount of LFO. And then we chuck that 5 seconds into now. This is while true. And then we spork this so that it's running in parallel with everything else that's happening. Okay, next, let's scroll down. We have our things where we chose oscillator 1 and oscillator 2. Now we have a similar thing where we can choose the LFO. If you send this to 0, then it unchucks all of the LFOs from both filter and pitch. If it's 1, then the sine goes to the filter and the pitch. Saw and square don't. If you send it 2, then a saw gets chucked to filter, LFO, and pitch, and sine and square don't. And if you send it to 3, then sine and saw don't, but square does. What else we got down here? I also added 2 more helper functions, one called pitch mod and one called cutoff mod. And those just make it so that you can choose from 0 to 100, and those are like normalized for useful values for those things. So I chose an 84 here because if you choose a square modulator for your LFO and then you crank it up to 100, then you get an octave jumping up and down. I just found that via trial and error. And 500 seemed like a good amount of filter LFO amount when it's maxed out. Okay, so now we got all these options. Let's hear what it's sounding like right now. Let's have our offset be 0. And let's see. We'll have our pitch mod be 1.5. And see what that sounds like with the patch that we had a little while ago. So that's you can hear that vibrato happening in your oscillator there. And if we turn the pitch mod back to 0, then you won't hear it anymore. Or if we set it to, like, let's say to we'll select a square wave, and then let's have a pitch mod of, let's say, 15. So that's why I wanted to go to 100, and if we switch that to 100, and of course, if we want to make this like really fast, and make this like set an alpha frequency for this to be like 12 hertz, then you're going to get like what else can we get? What else is interesting here? Okay, let's set this to like 3. We'll choose an LFO of 2. We'll make the the pitch mod 0, make the cutoff mod, let's set this to 50. And we'll set our cutoff to 10, see what that gets us. This might make it something noisy. Not sure. If we randomize our LFO frequency on that, then that might be good. Check that out. Let's detune these a little bit, and I'll just see what that sounds like, just like the detune. Starting to sound like a real synthesizer. And then let's make it off by a fifth, just because I love doing that. Let's change this to a 3. So you can hear how the resonance is interacting with that and the different frequencies. So yeah, we got our LFO working. Okay, next I added a noise source. This was the easiest thing. All I got to do is make a new noise, call it noise source, chuck it into the low pass filter. I set its gain to 0 by default, so you don't hear it when the synth turns on. And then I just made a picker, another helper utility here for choosing the amount, and I'm just multiplying 1 by the 0 to 100 thing that your user uses or selects. So by default, it's 0. And we're just going to use something similar to our last noise here. If we put the noise at 10, you can hear that it's adding a little top in there. And if you crank it up to 100, then you can hear it like so. And of course, we gave ourselves the option of turning off the oscillators 1 and 2 completely. And if we were to do that, then we just get the noise. Let's make our LFO type a square and see what that sounds like. So you can use our synth voice to make percussion. You can use it for hats and things like that. Noisy hats, noisy snares, that type of thing. I decided to punt on using a high pass inside the Chubgraph because it was acting really crazy. It was like distorting like nuts, and I don't really know why. But the high pass filter on a Moog Grandmother is not really a first class citizen. It's not patched in the signal chain. Normally, you have to actually do extra stuff in order for that to be patched in, which means that it's basically just as easy here as it is on the Moog Grandmother to patch it in manually here. So I just put one in between the voice and the DAC, and now it sounds like this. I set a 1000 to the frequency. So if you must, you can always extend a synth voice with a high pass after it as a patch. But yeah, it's really straightforward to add a high pass filter. Let's do 500 and see what that sounds like. Or we even go up as high as like 2000, see what that sounds like. And there might be cases where you'd want to do that. And then adding a reverb was extremely straightforward. Just right after the limiter, before it goes out of the outlet, just added in a reverb. And I made another helper function so that we could choose how much reverb there was. I decided that 0.2 should be the max, and normalized that so that the 100 gives us what we want. I changed our attack time so that we could have something that could showcase the reverb a little bit better. Here's what it sounds like when it's completely dry. And then we have, if we add, let's add 5. And let's do 50. It's kind of grungy, but it's kind of got a little bit of character to it. Let's make this even, let's double the speed of this, just for fun. Did I not save it? I didn't save it. Like, that's the same speed. It's because I didn't save it. Try now. Kind of cool. And then if we crank the reverb all the way up to 100, sounds like so. Let's put this back to 1 second divided by 2, and we'll also, let's add in some attack time, make it like 500, or make it 250, and then let's add a little bit of the, so we got our LFO, let's add that back in. We'll make that our pitch mod and see what that sounds like. And we'll back this back off a little bit. See what I'm just playing around. I'm noticing that this is like, we're really pushing the limiter hard, and it's making it sound a little distorted a lot of the time. I wonder if that would sound a little bit better if we push these all down to 0.1. See if I get a little less of that. Yeah, it's better. Maybe if we push this up to 8. I'm not sure what this is going to do. Sounds cool, though. And if we dial back the reverb a little bit, we can hear that. Let's dial this back down to 10. So the last thing that I did was I made a function called help, which spits out a bunch of documentation about what all these different functions do. Because as you can see, this thing gets got a little got pretty wordy by the end. This thing does a lot of different stuff. So to help ourselves out in the future, let's, whenever you add this thing to your ChucK machine, it will spit this help file out. And I broke out the actual usage of this thing into another file, which is here. It's called use.ck, and another file called initialize, which calls them in sequence. So this one grabs the synth voice and puts that in the ChucK VM, and this one uses it. So if I save this up and I call initialize, then we will see two things. We will see that it spits out the documentation and also that it plays use.ck. I'm going to add these to my GitHub repository. You're going to see a link here, and you're also going to see it in the description. So if you don't want to do all the typing that I did here, then you can just pull the files down. In this tutorial, we talked about Chubgraphs and how to make your own monosynth using Chubgraphs. In our next tutorial, we're going to take a look at some techniques that might work for live coding.